it's giving you a rate.
Mhm.
And when you integrate a rate, this is not really correct, but when you integrate a rate, you get some sort of a total quantity. In this case, it would be the upper units, the gallons.
Okay.
So we've seen rate problems like this where this is the consumption. Okay. And let's just maybe make this a little more interesting. So, you drive a car, I drive a car, we consume, but we also fill up.
Mhm.
So there's like, in this case, the fill up is the in, and this is the out. And we generally go, in that direction, in minus out.
Okay.
So let's just say the way that the in function, the I of t, let's say that's just it's well, I don't even know how many gallons per day. Let's go 100 gallons. Okay. Actually, that's gonna be too much. Let's say it gets 10 gallons a day. All right. So the rate here is I of t minus C of t. Okay. So if we just cared about C of t, which is what the problem asks, you would integrate from 0 to 7, 4 plus 0.001 t to the fourth dt. That's this part. Okay. And they say, okay, well, they say, well, do it by hand. You're like, all right, well, how do I do that? Just find your antiderivative. Okay. This one's a little harder. I mean, you can just divide by the new exponent like that, and then you evaluate from 0 to 7. And you get some number. Does it say to not use a calculator, or does it say a calculator is okay? Oh, set up. It's just a setup. Okay. So the rate, but if you want to get this one, you integrate this 10 dt from 0 to 7, and then you subtract this other part. So you get 10t evaluated from 0 to 7 minus all of this over here on the right. And you get some number.
Okay.
So that's your net change. Your net change is in minus out.
Okay.
And you get some sort of number. Is that clear?
Yeah.
Okay. Let's look at number 4 because it's just a setup problem.
Okay.
Okay, a 2-meter rod has a variable density modeled by the function rho of x equals 11 minus 4x grams per meter. I like putting units in brackets. So the 2 meters is important here. There's a rod, okay? It's basically saying like it changes with respect to where you are on the rod. So the mass in this case will be in grams because it's the top unit there. So the rate, and you're used to rates being like something per unit time. They don't have to be. The rates can be, in this case, it's mass per unit length. So a rate more generally is something per something.
Okay.
All right. And then just kind of the standard thing is you integrate. Okay. But they don't tell you it directly. They say, okay, it's 2-meter rod. So you integrate from 0 to 2. Okay. 11 minus 4x dx. So something like that.
Okay.
And you get it. This one you can actually do reasonably well. This is not to be confused with, you may have done some force or some like density work problems where you integrate like rho gh. I don't know if you remember. I don't know if you did any of those or not in this class, but this is not the same. These are separate types of problems.
Okay. Gotcha.
That that kind of takes over, or I'm sorry, that kind of like finishes up exercises 1 through 5, these net change problems. So maybe take a look at the odd ones on your own and see what you see. Okay, let me go to 8. Look at 8 next. So it does say you can use a graphing calculator. So I am going to graph these to just get the image, just to save us some times. You probably wouldn't get one this sophisticated because you would, you may not know what it looks like, and then it's hard to know how to evaluate. So
Yeah.
the graph of this is here, and I believe it just wants you to find the area enclosed. So that's this region here. Okay. Let's do, I don't know, do you want to do x-axis or y-axis here?
Um,
Because it doesn't matter. It's gonna be the same, but
Yeah.
it's different integration with what, x or y.
do X.
All right. Okay, so x, this is a disk problem.
Okay.
Shows numbers with a gray background, indicates problem that's side self-like. Okay, so this is a gray background. So it's going to integrate from 0 to 1 pi. Okay, and then we need our r here. So this is our r, which means we need to solve this for y. Okay, so you're gonna subtract the square root of x from both sides. So that gives you the square root of y equals 1 minus the square root of x. And then you square both sides like this, and you get 1 minus the square root of x squared. Right. And that's your y. So that's what goes here. Now we should expand this because we're going to have to expand it here. So let me I guess I'll write it here. 1 minus square root of x squared, and then you got another squared because it's this whole thing is your r dx. This is 1 minus square root of x times 1 minus square root of x, and then it's actually to the fourth, so it's whatever you get here we're going to square again. So this, it looks bad, but I mean, it does kind of work out okay, I guess. So it ends up being 1 minus 2 square root of x plus x, but then you square that. So it's essentially like multiplying it by itself. Yeah, and it probably looks worse than it actually is because this is doable. So you get 1 minus 2 square root of x plus x minus 2 square root of x plus 4x minus 2x to the 3 halves. So this one is x to the 1/2 times that. That's where the 3 halves comes from. And then you get another x minus 2x to the 3 halves plus x squared. So you end up, and we haven't even integrated yet, you integrate 0 to 1, 1 minus 4x to the 1/2 plus 6x minus 4x to the 3 halves plus x squared dx. And this is a fairly reasonable antiderivative. So there's a lot there, but it's doable.
Yeah. Okay.
So because they say you can use a graphing calculator to find the curve, it's not as realistic to what you might see on an exam question, because if we just graph it with something, you already kind of know what you're looking for. But let me graph this. All right, so let me get this graph up. All right, so let me snip this in. There it is. All right, so here we go, snipping it in. Just tighten this up a little bit. Okay. So the green is actually this first one here, and then the purple is the line. One of the things you can do here, which it works in this problem and it works in some, is if you got this on an exam and you obviously can't graph y squareds, and you can actually switch x and y.
Mhm.
So, and maybe you've seen this before, but you could do 4y equals x squared minus 4 and 4y equals x plus 16. And if you solve these for y, you end up getting the same graph, but just in the other orientation. It looks like
Okay.
this, like that. And you can just switch your axes. It's kind of a cheat, but does work.
Mhm.
So this one, if we're trying to find the area between, we have to do a y-axis integral this time. There's, if you try to do a top minus bottom, it just gets really awkward. So this one forces you to do that. That's why it's probably a good question for us to look at.
Okay.
That means you need to solve both for x.
Okay.
So you get x equals y squared minus 4 over 2, and x equals y plus 16 over 4. And then it's a right minus left integral. So you're integrating right minus left. So for us, that's going to be this one right here, y over 4 plus 4 minus y squared over 2 minus 2 dy. And we're going to integrate from, we got to go find the bounds. The bounds are from here to here.
Mhm.
You know, I made a mistake in the last problem. That wasn't a volume problem, was it? Let me get this right here. So it's the y axis here, minus 4 to 5. Okay, let's finish this one up, and I'll go back and I'll deal with the last one because I really bumbled that badly.
Okay.
So here you distribute the negative and maybe combine like terms and maybe write 1/4 y plus 6 minus 1/2 y squared.
Mhm.
And then you find your antiderivative. So I'll do this one first. Minus 1/6 y cubed plus 1/8 y squared plus 6y evaluated from minus 4 to 5, and you get some sort of a number there if you want to work that all the way through.
Okay.
All right, so I really bumbled this last one, and let's actually like deal with this. This is not a disk problem. So let me show you what changes. It's not a disk problem, which means you don't need that square and you don't need that square right there. So you actually just integrate from this step right here.
Okay.
And you don't need the pi. That's also wrong. So it's just this 1 minus 2 squared of x plus x dx.
Okay.
Which is, yes, a genuinely easier antiderivative and evaluation at the endpoints.
Yeah. Okay.
So one of the things I noticed when you like as you get like more difficult in the section here from like say 6 to 14, you don't need to do like 13 because it's just like probably too much. So maybe do, if you have time, do the ones that are earlier in each grouping.
Yeah. Okay.
12 is a good one because we actually can do this by hand, but you do have to know the change of this. This is a double angle formula. This is 2 sine x cosine x.
Yeah.
So the general thing to do is to set equal. 2 sine x equals 2 sine x cosine x. And then you and then you move this to the other side. You don't divide. Dividing is bad. It removes one of the solutions.
Mhm.
And then you actually factor 2 sine x, 1 minus cosine x equals 0. And then you set each of these equal to 0. And you got to keep in mind where you are. You're only on the top half of the unit circle. So you don't have to look for like all the possible ones, because this one's really where sine x equals 0. And this one's really where cosine x equals 1. So cosine x equals 1 when x equals 0. Sine x equals 0 at pi, at 0 and pi.
Okay.
I know it just gives it to you, and you can just do like top minus bottom, but there will be a problem where you have to find the bounds. That's why I showed you all this, because you may have to do something like this. Like maybe this is 2x equals,
Mhm.
2x squared times pi or something. Who
Yeah.
knows? Okay, so in terms of figuring out, well, which is the top and which is the bottom, I know you could graph this one, but let's just say you didn't. You'd want to pick something in between, like pi over 2.
Okay.
Okay, so 2, unless no, we already found that they only intersect at the endpoints. So you would be like, okay, what is y equals 2 sine pi over 2? And sine of pi over 2 is up here at 90 degrees. That's 1. So it's 2 times 1, which is 2. And then sine 2 times pi over 2, that's at pi, that's over here, that's -1. So we would probably say this is the top and this is the bottom.
Yeah.
Now, just to be certain, I'm going to use some technology here, which should help here. So we're going from 0 to pi, and then the other one is sine 2x, 0 to pi. Not that it really matters, but the image is kind of interesting for this. It reminds me of, I think it used to be a peace symbol. I don't know, but it's fine in this area between there. And so we did correctly identify top minus bottom.
Yeah.
I don't know if you're active on social media, but sometimes math people throw out, like on Valentine's Day, they did like a bunch of like, here's what a heart looks like, and
Yeah.
here's what other shapes, and
Yeah. Mhm.
it's actually easier just to freehand draw them than to try to find a function to make it, but that's what we've got here. So you're going to integrate your top function, which is 2 sine x minus. Now this is where you do not want to use this right here.
Okay.
You actually want to go back to the other one, and you might be thinking, well, why would I do that? And it's because it's easier to integrate this way. You can do both, but it's just a kind of a choice here. So as a reminder, you can separate these. So you can make 2 integrals.
Yeah.
And then this one right here is minus cosine x with a 2, 0 to pi. This on the right is actually a u substitution. But just for a moment here, let's remember the derivative. If it's minus cosine 2x, the derivative of minus cosine gets you back to sine. You keep the 2x, but then you would multiply by 2. So to undo that, you divide by 2 here.
Yeah.
And if you if you're get on exam, like I don't not sure about that, just do the u sub thing here, and it'll work out.
Okay.
So you get minus 2 cosine pi plus 2 cosine 0. This becomes a plus 1/2, and then you get cosine 2 pi minus cosine 0. One of the disadvantages of going this route is that you can get a lot more sign errors, because you got to remember it's top limit minus bottom limit, but then you got minuses there. This one became plus, but you still got to do top minus bottom limit inside here.
Yeah.
And so on. So this ends up being, let's see here. This is -2 times -1 plus 2 times 1 plus 1/2 cosine of -1, cosine of 0 is -1. So you get -1 here, 2 plus 2. Believe it or not, it works out really nicely.
Perfect. Okay.
All right, so that, to me, that takes care of like 6 through 14, kind of those types of problems. They, like, if you look at 16, 17, and 18, they just get more complicated. And they can be done by hand. They're just more work. Like 17 is good, a good problem by hand. But I mean, you have to tell me if you think we should do any more of those or move to like volumes.
Maybe one more
Okay.
just to get it down.
All right. So I'll do 18 because you have 17 available.
Okay.
Okay, the region enclosed by the graphs of this right here, they're giving you this window, but what they're not doing is they're not telling you like which one's the top and which one's the bottom. Now, maybe you realize like, oh, this is a quadratic and it opens up, so it's the bottom. Okay. And then, well, therefore this must be the top. But if you weren't sure, you could let x equal 0 and you just try it, even if you just want to confirm this is 3 to the 1, which is 3. And then the other one is 0 squared minus 3 over 10, which is minus 3 over 10. So then you're like, oh yeah, that's the top, that's the bottom.
Okay.
It appears that they intersect at -2 and 2. Although I wouldn't trust that. I would at least try those in here.
Yeah. Make sure.
Boy, I'm not even sure that's right, but okay. Because let's try this. 3 to the 1 minus 2 squared. That's over here. So that's 3 to the minus, what is that? Minus 3 power, 1 over 27. And then this other one would be 4 minus 3 over 10. Okay, so that's definitely not where they intersect. Does it say something here that these are calculator problems?
Let me look. I'm not sure. So that's weird. Yes, the when it has like the gray area around the number.
Those
means-
are calculator?
That means you can use a calculator, yeah.
Okay. So I'm graphing this in the other screen here, and I want to just see if like, because this will give me the nice, see, they don't intersect at nice points. I'll show that to you with a snip here. And that means to integrate it, you gotta use a calculator and know those bounds. Like, but the way the instructor could make this problem easier, they could also say, from -2 to 2, and then you're okay. But let me graph it here so you can see. You can see it's obvious it's not a nice value. And setting these equal isn't like, it's not like, oh, we'll just set them equal, Matthew. You're like, yeah, well, it doesn't really help. So the reason it doesn't help is if you want to get this out, you have to take a natural log of both sides. And then now you have the same problem again. You've got, where, okay, I got this out of the exponent. Now I got to separate this.
Yeah.
So it's bad. This has no solution by hand. There are ways to solve it, but it's numerical. So even that, what I just told you wouldn't have been right. You wouldn't have gone, you would go from like, let's just say it was -1 and 1. Okay. But this leads to a new problem. So you integrate from -1 to 1. Top is 3 to the 1 minus x squared minus the bottom, which is x squared minus 3 over 10. This one does not have a known antiderivative. Like the integral of a to the u, or I'm sorry, a to the, yeah, a to the u, du is a to the u divided by the natural log of u. But U has to be, I'm sorry, natural log of A. God, I've got this all messed up. Let me restart. Integral a to the x dx is itself divided by the natural log of A. This only works though if x is something nice, and
Yeah.
this one is not. So
Oh.
there's a technique called integration by parts, which you might see, or I guess maybe we did do a little bit, but this is a calculator problem.
Okay.
So you would get like the bounds from the graph, and you would do this top minus bottom,
Mhm.
and you would get your answer that way.
Yeah. Yeah. Okay.
Right. Okay, I'm going to move to 20,
Okay.
which is a first volume. Find the volume of the solid by revolving the region bounded by the x-axis, the curve y equals 3x to the fourth, and the lines x equals -1 and x equals 1 about the x-axis. So this 3x to the fourth, it has the shape of a parabola. And so we don't know exactly what it looks like, but if we were to do it by hand, we could test each of the endpoints in there. So like 3 times 1 to the fourth gives you 3, and 3 times -1 to the fourth also gives you 3. So it looks like this. It's this region there.
Okay.
And they want volume this time. So they don't just want you to do top minus bottom, but volume does, depending on the type, it could be top minus bottom, but this is a disk.
Yeah.
And disks are pi r squared. Your r is really the y in most cases. So this is the integral from -1 to 1 pi 3x to the fourth squared dx.
Yeah.
So the antiderivative is pretty nice here. Something like that.
Yeah.
All right, so you end up getting 2 pi when you're all done. Hopefully 20. Oh, where's 22? 22.
Oh, that one, it like had half of the problem on one page and the other half on another. It was hard to screenshot, so I just abandoned that one.
Got it. Let's do 24.
Okay. It was just too hard to screenshot, so I was like, well, there are other questions.
There's plenty of problems here. And even though I'm doing the even ones, there's enough online resources now that if you wanted, you can find the solutions to the odds pretty reasonably. So
I have the Quizlet Plus, so I have it where they like explain and show how people did it.
yes, that's very useful here. So this one, it's telling you that it's cross sections.
Mhm.
Okay, and they tell you they're a semicircle, and the diameter is the connecting the two graphs. There's a lot of explanation here to get this, but they say, okay, it's sine x and minus sine x. So sine starts high. I'm sorry, starts at 0 and it goes high and comes back down. I'm going to just exaggerate this slightly so we've got a little more room here.
Okay.
So this is pi over 2 and this is pi. Okay. And then minus sine x, it goes the other way. It comes down like that.
Okay.
Because it's obviously negative.
Mhm.
So just review your graphs of, you got your sine graph and you got your cosine graph. Just again, if you got time, just double check, what those look like. So this time it's a semicircle. So what I like to do is graph what they're telling us, which is the diameter connecting two graphs. And then I'd like to draw the actual thing here. Sorry, let me maximize this. I would actually draw the cross section that's telling me, and then I would say, well, what is the red? It's the diameter here.
Mhm.
And we need to find the area of of the semicircle. So this top minus bottom here is sine x minus sine x. So it becomes 2 sine x.
Yeah.
And so the radius, which is what we really care about, is 2 sine x divided by 2.
Okay.
And then the area of a semicircle is pi r squared divided by 2. So it's pi sine x squared divided by 2. And so this becomes pi over 2 sine squared x. And then you integrate from whatever it tells you. So in this case, 0 to pi. And it's the area of the cross section. So you don't have to put a pi out here. And there's a lot of pi's going on in this one. So it looks something like this. So when you're doing a cross section volume,
Yeah.
it's the integral of the area function dx. There's no pi. But with discs and washers, there is pi. And you don't know enough to do this by hand. You would have to use a trig substitution for one of the Pythagorean identities.
Okay.
So let me grab that real quick. And then if you later on want to do this, you can.
Okay.
This is emphasized in calculus 2, which may be coming, right? Have you heard back from any of the schools you're thinking about going to?
Yeah, so there's 4 schools that are my top ones right now, and I'm going to visit 2 next weekend. But my 4 right now are University of San Francisco, Tulane, Fordham, and the new school. So we'll see.
Where do you like want to go if you could go any? I mean, but
I
among
want
the
to go to New York City, which is where Fordham and the new
yeah,
school are. But if I don't like the schools enough to go to the city just for the city, I'm not going to go to the schools just for the city.
sure. Have you been to New York or San Francisco before?
Yeah, so I've been to all of the places. I visited 2
Okay.
this summer and I really liked it. So far, that's like the school I like the most. I don't know if I love
Yeah.
New Orleans as much as New York City,
Yes.
but I love San Francisco more than I love the school. We just visited last weekend.
Yeah,
So
the cities are very different than Tucson,
yeah,
obviously.
yeah, I obviously want to go to bigger city.
Yeah, there's a lot that just every time I used to go to San Francisco, I'd get a parking ticket. So it was such a pain to get around, but it's
Yeah,
really a nice place to be.
yeah, I loved it, and I probably wouldn't have a car, which is nice.
Yeah,
But,
easy to get around there.
yeah,
People have been doing it for a long time.
yeah. So I visit New York next weekend, so we'll see. After
Great,
that, I'll probably know.
great.
Yeah.
So the approach here, just to kind of close this problem out, is you would solve this for sine squared. This last one, so sine squared theta or sine squared x would be 1 minus cosine 2 theta or 2x divided by 2, and then you could use a u substitution for that part. But
Mhm.
you have to know these. Like you can't, it's like getting around the subway system of New York. You got to have a map or an app on your phone. You wouldn't know what to do otherwise. All right. So 28 moves us into arc length problems.
Okay.
It says perimeter. Perimeter means arc length.
Okay.
I think that I'm gonna just graph this real quick. They might have showed a picture of this earlier in the book.
Yeah.
I don't know how they differentiate between like this and the kissing fish. Let me snip in a graph here so you can see it. All right, so the perimeter obviously is the, all the way around this thing, figure 8, infinity symbol, bow tie. They're really saying find the length of the curve of one of them. and then double it.
Oh.
But you can also find the length of just one and then quadruple it, because there's all these symmetries that you can take advantage of here. Because this is the same as this, and this is the same as there. Lots and lots of symmetry. So arc length is the integral ds. ds is the square root of 1 plus the derivative dy dx squared. And I don't know, I don't really have a favorite here, so we're just gonna go with this one. So the y prime is 3x squared minus 1, and then you got to square it. So the derivative, or dy dx squared, is going to be 9x to the fourth minus 6x squared plus 1.
Yeah.
I'm trying to decide if this is one we can do by hand. It doesn't have the appearance of that at the moment. So let's just say, we'll forget about the bounds for a moment. It's the square root of 1 plus, and then I got to go grab this 9x to the fourth minus 6x squared plus 1. So this one becomes 9x to the fourth minus 6x squared plus 2. All right, so here's what could happen is this becomes minus 1 squared. No. No, that doesn't work. Sometimes these become things that work out nicely. This one doesn't have the appearance of that. Let me just check real quick and see if this factors.
Okay.
Sometimes they become perfect square trinomials, which is what I was kind of looking for here.
Yeah.
And
Did not happen.
this does not, but this one on the right is a perfect square trinomial. So that's why I'm sort of bothered by this, because it becomes the square root of 1 plus 3x minus 1 squared. I'm sorry, 3x squared minus 1 squared with the Gertie. But this right here is a trig substitution integral, but really horrible. Just look, check. Yeah, this one doesn't do anything good. Let me check one more thing here. 3x squared minus 1. This one also doesn't work out. So is this a calculator problem? I'm sorry for keep asking, but
No, it's okay. I'm not sure. Does it have the little? No, I don't think it is. Which is weird.
let me,
Yeah, I don't think it is because for the test, all the arc length problems are going to be not calculated.
right. But this one on the homework could be or not the homework, but on this page, this could be a calc. Like, I guess I'm trying to tell you that there's no way to do this by hand,
Okay.
this part. But if you do like 27, which is find the length of the arch, that one looks like it does work out by hand. When you take the derivative and you square it and you put it in to the thing, it actually does look pretty reasonable.
Okay.
So because there is some 1 plus u squareds integrals, but
So
this one
weird.
is not. It ends up being an arc sine, or well, actually there's some 1 over. This one doesn't seem to work as nicely, and then there's very few that do for arc length. But one of the techniques they give in other courses is the thing that comes under here. You end up completing the square or doing a perfect square trinomial, and it does work. Let me just look one more time here. Did I miss anything? 3x squared. Yeah. Maybe there's something here where if you do like top minus bottom, it works out. X cubed. This one minus that one. No. Makes it worse.
Yeah.
I think 2x, and you get 2 minus 6x,
A weird question.
yeah. Okay. But the important thing here is this: for arc length, it will probably be a setup problem. So make sure you remember this, or whatever variation is in your book on this one.
Okay. Got it.
All right, let's do 32. It's one of these work problems.
Okay.
Okay, so a rock climber is about to 100 newtons of equipment that has been hanging beneath on 40 meters of rope. So there's 100 newtons right here,
Mm-hmm.
and there's 40 meters of rope, and the rope has a density of 0.8 newtons per meter. So when you pull this up, you're always pulling the 100 newtons. That's always happening. But when you, and we're going to call this down here like x equals 0. At x equals 0, you're also pulling 40 times 0.8 newtons per meter of rope.
Okay.
So it ends up being 32. At the top, when x equals 40, you're now carrying just the 100 newtons, and the rope has gone to 0.
Okay.
So we did a couple of these problems, and the like the force function here is, well, you always have that 100 newtons, but sometimes, depending on where you're at, you have this 0.8, and it depends on where you're starting. It's 40 minus x. And this is really common. Like this is you generally see like the distance minus the value of x times this density,
Yeah.
rope density thing.
Yeah.
Okay. Now they start piecing this apart, like, because they want you to like differentiate between the two, but you could just integrate this to get your like part C. So part C, which is generally what you're asked to, you're going to integrate from 0 to 40, 100 plus 0.8 times 40 minus x dx. And that's your part C.
Okay.
Part A, though, if you go back, is they're like, well, what if you just pull the equipment, which is kind of, it's like, well, I can't pull the equipment, I got a rope attached to it. But they're like saying, somehow imagine you could just pull the equipment. So work most generally is force times distance. And in part A, the force is 100 newtons and the distance is 40 meters. So you get 4,000 newtons.
Okay.
And by the way, you get that here also.
Yeah.
Okay. Part B, you have to do with an integral. So part B is the integral from 0 to 40, 0.8, 40 minus x dx.
Okay.
And so they're in part C, they're saying we'll just add the two answers from A and B, which you can do, but you can also set it up all together. And I think we might have talked about a problem where you go like halfway up, or the second half, how much work is being done.
Mm-hmm.
Something like that.
Yeah.
So it seemed like you would get a function like this, a force function, and you have to derive it. They're all kind of the same. Sometimes they tell you, instead of telling you this number right here, they tell you that 40 meters of rope weighs something.
Yeah.
And then you have to divide to get this number right here.
Yeah. Okay. Make you do more work.
Grab 34 here. Stretching a spring. Let me just see if there's that word. I don't know if I missed that word. So the spring of it's the spring formula is F equals KX. And the force is 80 newtons. And the K, we don't know, but it's telling you it's 0.3 is the X right here.
Mhm.
So these problems, whenever you see a spring problem, you almost always have to start here with this. And K equals 80 divided by 0.3, which is 800 over 3. And it's got a units of newtons per meter. Watch out for problems where they give this to you in centimeters instead of meters, because then you have to cancel. Or not cancel, you have to convert.
Yeah.
All right, so that's your K. And the reason you need that is because you need to put it back into here because you're going to integrate.
Mhm.
Now it says, you know, and you know, you got to be careful of the language because it says, how much work does it take to stretch the spring this far? That's, we'll call that part A. That's going from its natural length 0 to 0.3.
Mhm.
And then you're gonna integrate this 800 over 3x dx. That's part A. Part B is they want you to stretch it an additional meter. So they're saying from 0.3 to 1.3. They are not saying from 0 to 1. And the answers are not the same.
Okay.
And that's because this is a linear function here. When you integrate it, you get a quadratic. So they're saying from 0.3 to 1.3, 800 over 3x dx.
Yeah. Okay.
And it seemed like you were going to get like each type. You're going to get one where you had to pull a rope, and then another where you were doing a spring. I think I saw in the last like pictures you sent, it was, those were the two types. You did send some pictures of like water being pumped out and so on. I would not spend any time working on those.
Okay. Yeah. They told us we're only gonna have 2 questions like this. So one will probably be a spring and one will probably be a
Yeah, the rope pulling,
yeah. Yeah.
yeah.
That makes
Um,
sense.
yeah, if you've ever, I mean, this is, I mean, if you ever climbed rocks, I mean, this is a big deal. I mean, that's why you limit how much stuff you bring because it gets heavy quick.
Yeah.
All right, well, that does take us to the end of our lesson for today. Thanks so much for scheduling. I hope you figure
Yeah.
out your college choice, and thanks for letting me help you. Hope you have
Thank
a
you.
great weekend, rest of your weekend.
You too. Bye.
Bye.